Okay, we start up. Today I just wanted to finish off this convergent-divergent nozzle thing with the shock waves and all that, because that's something you're going to fight with on the next exercise. And then we will start programming openFOAM, changing the source codes. So let's have a look. I have some numbers here. I'm not going to write everything down, but so you get an idea. If you look at only the convergent part, convergent nozzle, then we have a reservoir, infinitely big, and then we have a nice little converging nozzle, something like that. Of course, when you are going to fight this exercise, you don't have an infinite huge reservoir, so you are going to start here and then go through a convergent nozzle and then a divergent nozzle and then an opening. So for here we only take sort of the first part, and inside here we have say our reservoir and values. So we have a temperature, T0, pressure, we have the sound of speed, and then we have the density, something like that. And then also we have a velocity in here, which then should be 0. That's an infinite reservoir, so we don't have any velocity here. So hence everything here should then be say standard things. You can put this one to 1 atmosphere if you like, and then put some numbers here. Speed of sound then should be standard, 340 meters per second or something like that. But then we have an opening here, and here we have something pressure exit. And then speed of sound is going to change, density is going to change, temperature is going to change, everything is going to change. And also, of course, we're interested in finding the velocity there. Something like that. And then somewhere around here, big reservoir, big opening. Yeah, there we have, say, the reference pressure. And then if we look at, say, some different scenarios, 1 atmospheric pressure here, then we have some lower pressure here. So the difference will be the driving force in this problem. So if we then have 3 cases, then what did I put here? 0.6, 0.2, and 0 ATM. ATM. There we have it. And now you can start calculating if we do the following. It's isentropic. So the enthalpy is constant. It's a cheat. Yeah, we know that. It's not correct, but more or less not too far away. So it's adiabatic and it's reversible. So we don't lose energy here. This is okay, except, of course, close to the walls here. Here we have some question marks, of course. Sort of in a thin boundary layer there. It's not so good. Not to mention, if we experience shock waves, then this is not correct anymore. But here is more the question, can we achieve a shock? Will we get a shock here or not? Okay. So if we now test the first case, then from these isentropic relations we have gone through, you should then find the following. Now the driving force, or say this reference pressure we have here, that one is bigger than the necessary critical pressure to achieve a shock. No, we don't get a sonic or a supersonic flow. We will have a subsonic situation. And yes, you can find whatever you want. Then from these isotropic relations, what's the solution in this narrow opening? You will find a Mach number of 0.8 something, and well, everything should then be good to go. We have the solution for everything there. For the case B, then we're talking. Now that one is going to be smaller than this critical pressure. So now we will have, say, a choked nozzle. Choked. What does that mean? Well, as long as you go below this P star here at the exit, then you will achieve Mach number of 1 in the opening. And you can't get any higher. Choked. So the Mach number is 1 at the exit. Maybe we should call him Mach exit. Something like that. It will be really choked. And then from that one, then you can calculate everything else. Yeah, you can find whatever you want here, speed of sound, density, velocity, whatever. Of course, you know from this area velocity relation, Mach 1 can only happen in the narrow opening, in the most narrow opening, when the area doesn't change anymore. So the speed of sound is then, of course, going to be equal to the velocity, since we have Mach 1 at that location. So no problem there. And then finally, point C. Well, we have the same. And yes, it's also going to be choked in that situation. But now we will have some additional changes. What's going to happen here on the outside? Now we will have so strong a driving force, we will establish shock waves for this, say, big reservoir to the right. For this one, well, we will have a shock Mach 1 here, but nothing else sort of on the other side. Just be sort of a jet flowing out, no problem there. But with this one, we are going to get shock waves. We are going to get shock waves. And when it comes to shock waves, or actually expansion waves, then you can't use the theory anymore, because this one is not valid through a shock. So yeah, you're going to need some expansion waves, because the exit pressure here is so low that it doesn't match whatever reservoir pressure we have on the outside. So you're going to get some strange expansion shock waves, something like this. Expansion shock waves. That is what's supposed to happen. So say these three different scenarios is something that I will put up for you as tasks for the next exercise. And then we are going to use this, say, I'm going to put a divergent nozzle here as well. and then a reservoir. So you can simulate the shock wave structures actually. That should be the task. But I sort of wanted to check out that you can match no shock, then the velocity, he will accelerate through the convergent part, and then he will de-accelerate through the convergent part, of course. But when you come to these two, then something strange is going to happen. So the velocity will increase here, of course, continuity, but then the velocity is going to increase even when the area gets bigger and bigger. That's where we have the shocks. One point, say you want to simulate something like this. Fair enough. You have to put in these reference values in a reservoir. It's very, very boring to simulate an entire reservoir. It's too big. So we have to cheat somehow. We have to cheat somehow. How can we do that? Well, for the simulation, then say we are going to start here and then simulate the rest to the right here. But that means we have a pressure here, we have a velocity here, which should be the reservoir values, but of course they won't be. So how can we do that? Do it easy, do it easy. So say now you have to put in boundary conditions here. You would like to have the reservoir values, meaning zero velocity. That can't be done. So what are we going to do? Well, we will then here have to invent some, what should we call it? Pressure inlet, something like that. And for the boundary conditions in this problem, yeah, you have to put in this pressure inlet. You have to put in the reference pressure here on the outside. And then velocity, well, zero gradient. I mean, you are giving the driving force, so then the velocity is going to be a part of the solution. You can't put a driving force, a pressure difference, and a constant velocity here. That's not good. Then you're strangling the code. I mean, that's not possible. That's too much information. So you have to give him freedom to find the correct solution by himself, hence zero gradient on the velocity. Okay, fair enough. And then if you can sort of imagine trivial Bernoulli from somewhere inside this reservoir along a streamline hitting our inlet into this divergent nozzle. What do you get? Well, on this side you will have the pressure by density, and we don't have a velocity, we don't have any gravity here, no problem there, equals whatever you have here. Well, you will have this one, and then you will have plus the dynamic pressure velocity at the inlet squared half, just the dynamic pressure. So there you can have a coupling setting up this situation. You have to give this value as an inlet or say a boundary condition for the pressure, but I would like actually to have this one, but we can't. And then the solution will provide us, what will this velocity be? Okay, then you see you can adjust this value from the solution, but you're going to need the velocity. So just a coupling between these 2 points. Simple, Bernoulli, no losses, nothing. That should be the way to do it. Any questions to that one? That's okay. Okay, then have a look at the convergent-divergent nozzle. Strange. Convergent-divergent. So yeah, we have a nice geometry looking something like this. And then here we will sort of have our inlet. Actually should be the reservoir, but we can't simulate an entire reservoir, so we cheat. We create some inlet values there. Constant pressure. And yeah, the velocity then has to find himself a value there from the solution. Fair enough. And then here you sort of have the narrowest opening where the area doesn't change anymore. So that's the location we can find Mach 1 if the driving force is big enough. So way over here we had then the P0. Then of course we have to operate with a P inlet here. A little bit difference, but not shouldn't be too much. We will have an P exit here, and then over here we will have a big reservoir with a reference pressure. So to simulate this, then you are going to do the following. Put a symmetry line here, like that. Just simulating the upper half. You have to create this, say, curved wall there. And then we have a solid wall here as well, somewhere up here. And then we just put a symmetry line up here. And then here we will have an outlet. And of course we will say PA for this outlet. And yeah, this area has to be somewhat big because the shock structures is going to sort of expand and develop in this range before he flows out. So this should be your geometry. And well, if it's choked, you have strong enough driving force, then yeah, in this area here you will have Mach number to be 1. The question is what's going to happen afterwards when you are in this region. So well, we can make a little sketch here. Let's see now. If you look at the following, we have a Mach number, and then here we will have the area, critical area by the actual area. What's then going to happen when you start somewhere here? Well, you will get something like this. And then it's a question, will you reach 1 or not? If the driving force is strong enough, then yeah, then we can have a choked nozzle. If it's not, then he's going to sort of stop here somewhere. So then, yeah, he can go up here. Velocity is increasing. But then on the other side, well, then the velocity is going to decrease. He goes back again. But if the driving force is strong enough, then you will actually have something like this. Then the velocity will actually increase on the other side. He will go here. So there we have Mach 1. And then we will have a supersonic situation. Meaning the velocity, he's going to increase all the time, even when the nozzle is expanding. And then it's a question, what's going to happen here? We will have a pressure, say, pressure exit here. Now this one may be way too low to reach or sort of to meet naturally the surrounding reservoir pressure PA. And then, yes, to do that, you're going to get a shock. Shock or expansion waves. So we have a sudden change in this expansion, no, sorry, the exit pressure at that location. Let's see, I'm going to need some more space here. Yeah, we can leave that one. So, if we now look at, say, the pressure scale with this reservoir pressure that we have all the way over here, the critical value from our isentropic relations, that was 0.528 or something like that. Say 0.528 here. And then we have this location here. So what's going to happen? Well, ideally, this value then should be the same as that one. It's going to be a little bit of difference, but never mind. So I call him 1. He's actually a little bit lower, but never mind. So what's going to happen? Well, the pressure is going to go down when you have the flow inside this divergent nozzle. Of course it is. Speed goes up, pressure goes down, as it always will. And then, if the driving force is not strong enough, well, you have the lowest pressure in the narrowest opening, and then the pressure is just going to go up again, and then all the way over here is going to find the P atmosphere, or P reference, or whatever you call it. So the tiny little pressure difference here, that's the driving force. Not strong enough to create a shock. So that one is good enough. If we, say, lower this one, you might get a situation looking something like this. Let's see now. We start with 1 again. But now I reach 1 in the narrowest opening. I choke it. I have a Mach number of 1. But the driving force is not strong enough to create shock waves at the exit. Then what's going to happen? Well, then the pressure is just going to go up again on the other side. But then, if we increase the driving force even further, then all of a sudden we can have a solution looking something like this. But he has to meet this surrounding pressure here somewhere. Okay. Goink. There you have it. He has to do something. And the only way he can do that is through a shock. So yes, then you will have a shock wave. Then all of a sudden jump, then you call it supersonic. This is what definitely should happen. Where it's going to happen, how it's going to happen, we have no idea. We can't calculate this one by our equation system. They break down. Yeah.
Isn't PA kind of like the driving force, but it's still the same value for those parts? Or?
Yeah, I mean, you have the difference between those two. Yeah. From a reservoir here and then say all the way to the exit here. But just for this drawing, I use the same say level. Your choice if you change that one or that one is the difference that makes matter. Yeah. Yeah. Other questions? So the calculation by hand is sort of dependent on our assumptions here. Isentropic, meaning we have no friction, viscosity is 0. We don't have any heat exchange at all. So I say the diffusion coefficient, heat diffusion coefficient, is going to be 0. We don't have any anything, any heat exchange with the surroundings, adiabatic. So this is sort of our adiabatic setup, meaning the entropy is constant. Then it's possible to do this analysis. We can use this thermodynamic relations, but sooner or later this is going to break up, of course. So production of this entropy, what did we use? H? I think that's the letter they use in openFOAM. Production of this entropy. We have a couple of terms that creates it. Of course, we have this one, the viscous term, dx, dy, or whatever, something like that. That one is going to create some entropy. And then, of course, we have the heat, and then we will have the temperature gradient here. I think it's squared. So these two, yes, sooner or later they will going to show up, and then our theory on pen and paper breaks down. You can find a solution looking into tables. You find a lot of these shock tables. But we are going to simulate this and see what happens. So this means in this area here, close to the walls, it's actually not valid. Not to mention, if you get some nice shock wave structures here, then this one will always break down. But it should be possible to simulate it. I mean, the equations that we achieved, very easy, very simple, Euler equations, no heat, then it's very simple, but of course they have their limitations. So 3 different scenarios, that's what I want for this next exercise. Any questions to that one? Yeah.
How can the entropy be constant?
Here you don't have any change in entropy when you do this simplification. So that's the point. But in real life, I mean, you know, we cheat all the time, as much as we can, yeah. Other questions? That was a little too soon. That was a little too soon. Up again. Now, programming in openFOAM, changing the source codes, creating your own version of some programs, little C++ programming, piece of cake. Now let's have a look at some scenarios. I'm going to use the classical cavity case, where you have square box. This is moving with a velocity of 1 meters per second, and we have a nice big vortex. And the classical cavity setup, it was 0, 0 location down here, and then it was 0.1, 0.1. And then it was a two-dimensional problem. What I want during a simulation, during a startup of this cavity, laminar, nice, easy, but transient, I want to have a velocity up here, just below the moving wall there. I want to trace that one as a function of time. So what should we call him? My point. And what will the location of my point be? Something like this. In x, 0.05. And then in the y direction, 0.099 or something like that, just under the moving wall. And then in the z direction, if I recall correctly, by default, it was 0, and then it was 0.01. Then I want a location just in between, 0.005. That should be a good location. Of course, you could use a probe or something like that in a post-processing way to find this velocity at that point at all given times. Never mind that, we are going to program that one. That's the whole point. Let's see now if we can make this one work again. Here we go. Something is wrong with the setup here, but never mind that. So here we are in our openFOAM. We have a nice run folder. And here is all your cases. And I think I have a classical cavity case here. Let's have a look. Cavity. Yeah. I think this one is the original. So yeah, I'm going to simulate that one. But I want to print out for the velocity at that location. So how to achieve that one? Well, openFOAM has been built for people with itchy programming fingers. So yeah, you are allowed to play around with the source codes as you like. You can create your own versions. And it's safe. You don't mess around with the original. You make your own local copy. And then you can do whatever you want. So let's have a start. First, we have to create sort of a working folder. Let's see now, I'm standing in my run folder within a cavity case. That's fair enough. Never mind where you're standing. Make directory. This command is only to be executed once. This one will now create a directory structure where you can play around with your own, say, source code versions of the openFOAM. And we have the $WM underscore project, and then we have a user directory. Under that one, I want to create solvers. I want to create incompressible. Something like that. And yeah, that should be enough. Make directory -p. He will create the entire directory structure for you. This address should then be the location just below your run folder. So it should be this address here. Let's try that one, see what happens. Okay, let's see now. I go to my run folder. And then I go one step above. Then, no, that was wrong. Run we solvers. I missed something. My mistake. We need the application as well. Well, let's fix that one. Remove the solvers and then do it again. But I wanted to have application. Applications. There we have it. So from this, say, basis folder, we are now have applications, solvers, and then I choose incompressible because I'm going to play with the openFOAM. Now it should be correct. Yep. There I have my applications. Fair enough. So now we can edit that one. Change directory, application, solvers, incompressible. I mean, they are unique. There's nothing in them. They're just empty folders for now. So now I'm standing in my incompressible folders. Copy the source code. Copy the source code. Copy. And then the entire folder structure. Copy -R. Where do we find the source code? Well, that one should be in the address $foam _up. So that one should be the location for all your different source codes. And under that one, well, I want solvers. I want the incompressible, and I want the openFOAM. Copy that one to where I am standing. Let's see if that one works. Yeah, seems to be working okay. If you are in doubt of these addresses, these $foam and $WM, yada yada yada, if you wonder where they are, you can write echo, and then you have say foam _up. Then you can actually see the location for your distribution. Where is this one actually located? And then of course you can use the direct address instead of using these aliases, but your choice, your choice. So now I have copied the files, the openFOAM source code. So let's have a look at that one. Change directory. What do we have here? I have 2 files, and then actually I have an entire folder. What's this? They are not big. Disk usage -H. You can see for yourself they are hardly anything. Very small indeed. Make, that is an important thing. When you create a program under Linux systems, the make is a script that you are going to love. I mean, when you create a program, a big one, you will have maybe 100 different source codes, a lot of different files, as we have in openFOAM. And then you're going to create an executable. How do you do that? You have to compile everything. When you compile a source code, he doesn't create an executable directly. He will first create what we call an object file. And when you have done that with all your 100 files, then in the end you can link it all together into one single executable program. So you have it in 2 steps. But with make, he's very smart. Say you have a big program, 100 files, but you have already compiled 99 of them. You have only changed a little bit in one file. Then the make script, he will detect that, you only changed one file. Then I will only compile that one and then link. He will sort of detect the changes. Because if you're going to compile the entire openFOAM program, it's going to take hours. But just change one file, that is piece of cake. I'll show you. Let's have a look at this make folder. Under make, we have two files. One is called files, one is called options. Let's have a look at the files first. Here we are. Not much information. First entry, that's the name of the C++ file, the source code. And the second sentence, or actually the third one there, that's the name of the executable. And here comes something very essential. This is the original. So the address where he is going to put the executable, if you compile and link OK, then you shouldn't destroy the original. I don't even think you're allowed. I think that one is protected. You can't overwrite him anyway. So you have to change him. And the whole point here is you have to change him into your own personal area. So you have to add _user in that file. That is a crucial step. Without that one, nothing will work. But now you can create your own version in your own area, in your own playground, and you don't destroy the original. But that one has to be done. Quite essential, quite essential. So that's the first important step. Okay, any questions so far? I see we have the clock already. Yeah?
What version are you running?
I think it's called 2312. That's my version. But I think you should have the same. I don't think they have changed this source code setup much. So even version 11 or 12 should be okay. Yeah. Okay, let's take a break then before we continue.